Hi, in this video, we're going to be working in section 14.2. We're going to talk about the regression equation. So as we discussed in 14.1, variables can relate with each other in different ways. I'm going to share my screen, looking at the notes, chapter 14. This is on page 6, excuse me. So we see that there are several different types of relationships between two variables. Relationship can be linear when we plot it on a scatter diagram or a scatter plot. And in this case, we have that positive linear relationship or that positive slope. As one variable increases, the other tends to increase. And over here, we have this negative relationship or this negative slope. A relationship can be nonlinear. So these are two examples of two linear relationships. A relationship can be nonlinear when plotted on a scatter plot and the points follow a pattern, but not a line, right? So we can see here that sometimes you might have a y variable that increases and then decreases. This might be an example of if you ever went in the old days when we would crowd into Dunkin' Donuts, right? If there were maybe 2 or 3 servers at Dunkin' Donuts and you went in to get a coffee, then they were probably pretty efficient. But as the number of servers, so if the x-axis is number of servers here and the y-axis is number of coffees sold, you might find that you're working just fine. You're faster with 3 than 2. But if you get to 15 or 16 people behind there, they're just going to be bumping into each other, and the number of coffees they serve is actually going to decrease. So this is a relationship that you actually see in business often. And then these other just general kind of nonlinear relationships, which we can see in data. So a relationship has no correlation. When plotted on a scatter plot, the patterns do not show, the points do not show a pattern. So some kind of cloud-like behavior here. This would be no relation. Okay, and I just wanted to build some intuition around how data looks in scatter plots. So I'm going to present to you some pictures, and we're just going to start to look at them and get a feeling around these scatter plots. So here are two variables. One is grip strength and arm strength measured by 2 independent measurements for one individual. Like you're going to press something to get your grip strength, and then you're going to lift to get your arm strength. And we can see that folks maybe that have less grip strength might also have less arm strength, but it's not really a perfect straight line. It's just this tendency that people with stronger grip have stronger arms. There can also be a negative relationship. One example is if you look at the elevation, if you're climbing the mountain, and the temperature. So the higher you get, the cooler it gets as you get to the top of the mountain or higher up in the mountain. Here is an example of a nonlinear relationship. So if I'm looking at, if we look at fish and we look at the length of the fish, and then we also weigh the fish to find how many grams that fish, or you could use ounces, but to see how much the fish weighs. What happens is, as the fish gets bigger, if you get a fish that's twice as long, there are some fishes, right, like little skinny eels that maybe, well, I should not speak specifically about fishes and species because I probably don't know it. But what I do know is that if you get bigger, if the fish gets twice as long, he has a tendency to also, he's going to get wider and deeper as well, at least in parts of the body. And so that this doesn't grow up linearly, but it does have this sort of like increase more, more quickly than a linear relationship. So the linearity would, a linear relationship might extend out in a straight line from the smallest, but you see that these fishes are getting heavier faster than they're getting longer. Okay, so here's an example of two variables that have no relationship. If you look at boys' heights and the birth month that they were born in, you might not see very much relationship. Okay, so we do see that we have relationships. Then I would like to learn, and I would like us to learn how to quantify them, how to write down equations and calculations that clarify how good a relationship is, what the relationship is, if we can use it for prediction. All right, so we have to get a little more quantitative now, and we're going to find, we have these 4 observations, and I'm going to put them on a scatter plot. And so here they are. So 1, 1, 1, 2, 2, 2. Okay, so here's the point 1, 1. Here's the point 1, 2. Here's the point 2, 2. And up here we have the final point of 4, 6. So our job right now is to learn how to discuss how lines, what is the best line to fit this data. So I show you 2 candidates, okay? We have candidate A, which is line A, right? And we have candidate B, who is line B right over here. And I have these lines drawn, these on the graphs. And I'd like you to take a minute and just look and see which one you think fits better, because they're both really in there. They're both in the middle of all the data. So which line fits better, A or B? Okay, so I haven't really told you how we define how well a line fits to the data. So there really isn't an exact answer, but that's what we're going to move into now. So which line fits better, A or B? That depends on how we define a better fit. Okay, so what we're going to do is we're going to go ahead and use some of the notation and some of the stuff that we had looked at over in the weight of the books and the pages, right? So we have this little hat notation. So y hat denotes the y value predicted by a straight line for a value of x. And so when we put x equals 2 into our equation A, we say that we have 0.5 plus 1.25 times 2, or y hat is equal to 3. And let's look at it over here. So for line A, when x equals 2, I go straight up here and it predicts y equals 3. Okay, if I come down here, I'm sorry, that was line B at x equals 2. Y hat is 3 for line A at x equals 2. Okay, so just starting over with this, at x equals 2 in line A, the algebra gave us 2.25 plus 0.5. 2.5 plus 0.5, which was 3. And we can see that here by going straight up and over. And the grid lines help me get a little better at this. So for line A, we did see that y hat is 3. And for line B at x equals 2, we're going to go straight up. And notice that it crosses just not really at the point of 3, at the height of 3, but just below it. And it gives us over here 2.75, yes. Okay, so that's the visual, that's the graphical. We really have to rely on the equations whenever we can. And so now we want to talk about the error or the residual. error E equals y minus y hat. And for this point, we're looking at this one point here where the true y is equal to 2. But for line A, y hat was 3. Okay, and the true y is 2 for here, minus 3. So y minus y hat is minus 1. So if we come back here, we can see that this is the value of y, and over here at 3, that's the value of y hat, and that there is a difference of 1. Okay, and over here, y is still 2, but y hat was 2.75. So the difference was less, okay? So the difference is actually negative. The differences are negative, the points are below the lines. And we get line B has an error of minus 0.75. Line A had the error of minus 1. So we see that for the point x equals 2, line B is better than line A. And now if we think about, and this is the picture, that's kind of important in understanding how we see errors on a graph. So wherever your point is, that's the observed value of y. And in this case, the point is above the line. So the predicted value of y is down here. Y minus y hat is the error. Okay, so this is the error in the model. So we're going to say that the best line minimizes the total error. And here is where I'm going to be giving you showing you some formulas, but these are formulas that we won't really be working with, but I do want you to have to know what they are, because you might see them again, setting you up for future courses in research methods or even in applied statistics. So what we say is the best line minimizes the total error. And all right, so I just popped one of the pictures, the B line, into Paint, just so that maybe I can show you a little better about the errors. We saw here that for line B, change my color to green. So this is my actual Y value, right? So there's my Y value. I didn't change the color to green. All right, we'll just work with black. So this is the actual Y value. Here, and then this is the fitted value. So it was 2 and 2.75. And then we have this vertical distance of 0.75. Each of these points has a little, so that's the error that we're making. So we're just going to try to have a straight line. Ooh, I can actually do that. Okay, so bring this over here. That's the actual Y value. Bring it over here, you could actually see it, right? And then the fitted value is this other thing, is this other value here at 6. So then the difference is going to be the vertical distance. So each of these points has a distance. Some of the distances are below. Some of the points fall below and they have negative distances, and some of the points fall above and they have positive distances. But how well a line fits the points has to do with how we combine all of these distances. So what we want to do is we want to add up all the distances, but some of them, what's going on is that sometimes the distances are positive and sometimes the distances are negative, right? So for all the points that are above the axis, for all the points that are above the line, y minus y hat is going to be negative. And for all the points that are below the line, y, I take that back in reverse. For all the points that are above the line, y minus y hat is positive. And for all the points that are below the line, y minus y hat will be negative. So if we just added up all of these points, then they would, a lot of the distance that the point was from the line would cancel each other out. So what we need to do then is either take absolute values or square them or do something when we add them up. So we're going, for mathematical tractability, we're going to go ahead and square those errors. So the line having the smaller sum of squared errors fits the data best. In this case, line B, using this criteria, and I'm not going to go through it on the video here, but line B fits line A better. And so that's to say that if I consider all the vertical errors here and I square them, line A is going to have a bigger value than if I look at all the vertical errors here and I square them and add them up. Okay, so that is our best fit line. The least square criteria is the straight line that fits the data points best. It is the one having the smallest possible sum of squared errors. Okay, the regression line is the straight line that fits the data best according to the least square criteria. So it turns out that the regression line B, the line B is not just better than A, but it is the best possible line, and that any other line in the plane would cause a larger sum of squared errors. All right. Here are the formulas to calculate the parameters B0 and B1. And except for maybe one problem over in the StatCrunch homework in the my stat lab, I will be giving you these values. So we don't have them included in the formula card because we won't be working with them when we're working with our calculators. Okay. So I just want to move forward. Actually, I'm going to wrap this video up, and then next video we'll jump into an example. And I'll see you in the next video.